Section 1.6, Significant Figures. Learning Objectives. By the end of this section, you will be able to 1. Determine the correct number of significant figures for the result of a computation. 2. Describe the relationship between the concepts of accuracy, precision, uncertainty, and discrepancy. 3. Calculate the percent uncertainty of a measurement, given its value and its uncertainty. 4. Determine the uncertainty of the result of a computation involving quantities with given uncertainties. Figure 1.11 shows two instruments used to measure the mass of an object. The digital scale has mostly replaced the double pan balance in physics labs because it gives more accurate and precise measurements. But what exactly do we mean by accurate and precise? Aren't they the same thing? In this section we examine in detail the process of making and reporting a measurement. Figure 1.11. A double pan mechanical balance is used to compare different masses. Usually an object with unknown mass is placed in one pan and objects of known mass are placed in the other pan. When the bar that connects the two pans is horizontal, then the masses in both pans are equal. The known masses are typically metal cylinders of standard mass such as 1 gram, 10 gram, and 100 gram. B. Many mechanical balances, such as double pan balances, have been replaced by digital scales, which can typically measure the mass of an object more precisely. A mechanical balance may read only the mass of an object to the nearest tenth of a gram, but many digital scales can measure the mass of an object up to the nearest thousandth of a gram. Credit A. Modification of work by Serge Melki. Credit B. Modification of work by Karol Jakubik. 1.6.1. Accuracy and precision of a measurement. Science is based on observation and experiment, that is, on measurements. Accuracy is how close a measurement is to the accepted reference value for that measurement. For example, let's say we want to measure the length of standard printer paper. The packaging in which we purchased the paper states that it is 11.0 inch long. We then measure the length of the paper 3 times and obtain the following measurements: 11.1 inch, 11.2 inch, and 10.9 inch. These measurements are quite accurate because they are very close to the reference value of 11.0 inch. In contrast, if we had obtained a measurement of 12 inch, our measurement would not be very accurate. Notice that the concept of accuracy requires that an accepted reference value be given. The precision of measurements refers to how close the agreement is between repeated independent measurements, which are repeated under the same conditions. Consider the example of the paper measurements. The precision of the measurements refers to the spread of the measured values. One way to analyze the precision of the measurements is to determine the range, or difference, between the lowest and the highest measured values. In this case, the lowest value was 10.9 inch and the highest value was 11.2 inch. Thus, the measured values deviated from each other by, at most, 0.3 inch. These measurements were relatively precise because they did not vary too much in value. However, if the measured values had been 10.9 inch, 11.1 inch, and 11.9 inch, then the measurements would not be very precise because there would be significant variation from one measurement to another. Notice that the concept of precision depends only on the actual measurements acquired and does not depend on an accepted reference value. The measurements in the paper example are both accurate and precise, but in some cases, measurements are accurate but not precise, or they are precise but not accurate. Let's consider an example of a GPS attempting to locate the position of a restaurant in a city. Think of the restaurant location as existing at the center of a bullseye target and think of each GPS attempt to locate the restaurant as a black dot. In Figure 1.12a, we see the GPS measurements are spread out far apart from each other, but they are all relatively close to the actual location of the restaurant at the center of the target. This indicates a low precision, high accuracy measuring system. However, in Figure 1.12b, the GPS measurements are concentrated quite closely to one another, but they are far away from the target location. This indicates a high precision, low accuracy measuring system. Figure 1.12. A. High accuracy, low precision. B. Low accuracy, high precision. The black dots represent each attempt to pinpoint the location of the restaurant. A. The dots are spread out quite far apart from one another, indicating low precision, but they are each rather close to the actual location of the restaurant, indicating high accuracy. B. The dots are concentrated rather closely to one another, indicating high precision, but they are rather far away from the actual location of the restaurant, indicating low accuracy. Credit A and Credit B. Modification of works by Dark Evil, Wikimedia Commons. 1.6.2. Accuracy, precision, uncertainty, and discrepancy. The precision of a measuring system is related to the uncertainty in the measurements, whereas the accuracy is related to the discrepancy from the accepted reference value. Uncertainty is a quantitative measure of how much your measured values deviate from one another. There are many different methods of calculating uncertainty, each of which is appropriate to different situations. Some examples include taking the range, that is, the biggest less the smallest, or finding the standard deviation of the measurements. Discrepancy, or measurement error, is the difference between the measured value and a given standard or expected value. If the measurements are not very precise, then the uncertainty of the values is high. If the measurements are not very accurate, then the discrepancy of the values is high. Recall our example of measuring paper length. We obtained measurements of 11.1 inch, 11.2 inch, and 10.9 inch, and the accepted value was 11.0 inch. We might average the three measurements to say our best guess is 11.1 inch. In this case, our discrepancy is 11.1 minus 11.0 equals 0.1 inch, which provides a quantitative measure of accuracy. We might calculate the uncertainty in our best guess by using the range of our measured values, 0.3 inch. Then we would say the length of the paper is 11.1 inch, plus or minus 0.3 inch. The uncertainty in a measurement, A, is often denoted as delta A, red delta A. So the measurement result would be recorded as A, plus or minus, delta A. Returning to our paper example, the measured length of the paper could be expressed as 11.1, plus or minus, 0.3 inch. Since the discrepancy of 0.1 inch is less than the uncertainty of 0.3 inch, we might say the measured value agrees with the accepted reference value to within experimental uncertainty. Some factors that contribute to uncertainty in a measurement include the following. 1. Limitations of the measuring device. 2. The skill of the person taking the measurement. 3. Irregularities in the object being measured. 4. Any other factors that affect the outcome, highly dependent on the situation. In our example, such factors contributing to the uncertainty could be the smallest division on the ruler is 1/16 inch. The person using the ruler has bad eyesight, the ruler is worn down on one end, or one side of the paper is slightly longer than the other. At any rate, the uncertainty in a measurement must be calculated to quantify its precision. If a reference value is known, it makes sense to calculate the discrepancy as well to quantify its accuracy. A. Percent uncertainty. Another method of expressing uncertainty is as a percent of the measured value. If a measurement A is expressed with uncertainty delta A, the percent uncertainty is defined as percent uncertainty equals delta A over A multiplied by 100%. Example 1.7. Calculating percent uncertainty. A bag of apples. A grocery store sells 5 pounds bags of apples. Let's say we purchase 4 bags during the course of a month and weigh the bags each time. We obtain the following measurements. 1. Week 1 weight, 4.8 pound. 2. Week 2 weight, 5.3 pound. 3. Week 3 weight, 4.9 pound. 4. Week 4 weight, 5.4 pound. We then determine the average weight of the 5 pounds bag of apples is 5.1, plus or minus, 0.2 pound. What is the percent uncertainty of the bag's weight? Strategy. First, observe that the average value of the bag's weight, A, is 5.1 pound. The uncertainty in this value, delta A, is 0.2 pound. We can use the following equation to determine the percent uncertainty of the weight. Percent uncertainty equals delta A over A multiplied by 100%. 1.1. Solution. Substitute the values into the equation. Percent uncertainty equals delta A over A multiplied by 100% equals 0.2 pounds over 5.1 pounds multiplied by 100% equals 3.9%, approximately equals 4%. Significance. We can conclude the average weight of a bag of apples from this store is 5.1 pounds, plus or minus 4%. Notice the percent uncertainty is dimensionless because the units of weight in delta A equals 0.2 pounds cancelled those in A equals 5.1 pounds when we took the ratio. 1.8. Check your understanding. A high school track coach has just purchased a new stopwatch. The stopwatch manual states the stopwatch has an uncertainty of plus or minus 0.05 second. Runners on the track coach's team regularly clock 100-meter sprints of 11.49 second to 15.01 second. At the school's last track meet, the first-place sprinter came in at 12.04 second and the second-place sprinter came in at 12.07 second. Will the coach's new stopwatch be helpful in timing the sprint team? Why or why not? B. Uncertainties in calculations. Uncertainty exists in anything calculated from measured quantities. For example, the area of a floor calculated from measurements of its length and width has an uncertainty because the length and width have uncertainties. How big is the uncertainty in something you calculate by multiplication or division? If the measurements going into the calculation have small uncertainties, a few percent or less, then the method of adding percents can be used for multiplication or division. This method states the percent uncertainty in a quantity calculated by multiplication or division is the sum of the percent uncertainties in the items used to make the calculation. For example, if a floor has a length of 4.00 meter and a width of 3.00 meter, with uncertainties of 2% and 1%, respectively, then the area of the floor is 12.0 meters squared and has an uncertainty of 3%. Expressed as an area, this is 0.36 meters squared, open bracket, 12.0 meters squared, multiplied by 0.03, closed bracket, which we round to 0.4 meters squared since the area of the floor is given to 1/10 of a square meter. 1.6.3. Precision of measuring tools and significant figures. An important factor in the precision of measurements involves the precision of the measuring tool. In general, a precise measuring tool is one that can measure values in very small increments. For example, a standard ruler can measure length to the nearest millimeter, whereas a caliper can measure length to the nearest 0.01 millimeter. The caliper is a more precise measuring tool because it can measure extremely small differences in length. The more precise the measuring tool, the more precise the measurements. When we express measured values, we can only list as many digits as we measured initially with our measuring tool. For example, if we use a standard ruler to measure the length of a stick, we may measure it to be 36.7 centimeter. We can't express this value as 36.71 centimeter because our measuring tool is not precise enough to measure 1/100th of a centimeter. It should be noted that the last digit in a measured value has been estimated in some way by the person performing the measurement. For example, the person measuring the length of a stick with a ruler notices the stick length seems to be somewhere in between 36.6 centimeter and 36.7 centimeter, and he or she must estimate the value of the last digit. Using the method of significant figures, the rule is that the last digit written down in a measurement is the first digit with some uncertainty. To determine the number of significant digits in a value, start with the first measured value at the left and count the number of digits through the last digit written on the right. For example, the measured value 36.7 centimeter has 3 digits, or 3 significant figures. Significant figures indicate the precision of the measuring tool used to measure a value. A. Zeros. Special consideration is given to zeros when counting significant figures. The zeros in 0.053 are not significant because they are placeholders that locate the decimal point. There are 2 significant figures in 0.053. The zeros in 10.053 are not placeholders, they are significant. This number has 5 significant figures. The zeros in 1300 may or may not be significant, depending on the style of writing numbers. They could mean the number is known to the last digit, or they could be placeholders. So 1300 could have 2, 3, or 4 significant figures. To avoid this ambiguity, we should write 1300 in scientific notation as 1.3 multiplied by 10 to the power of 3, 1.30 multiplied by 10 to the power of 3, or 1.300 multiplied by 10 to the power of 3, depending on whether it has 2, 3, or 4 significant figures. Zeros are significant except when they serve only as placeholders. B. Significant figures in calculations. When combining measurements with different degrees of precision, the number of significant digits in the final answer can be no greater than the number of significant digits in the least precise measured value. There are 2 different rules, one for multiplication and division and the other for addition and subtraction. 1. For multiplication and division, the result should have the same number of significant figures as the quantity with the least number of significant figures entering into the calculation. For example, the area of a circle can be calculated from its radius using A equals pi r squared. Let's see how many significant figures the area has if the radius has only 2, say, r equals 1.2 meter. Using a calculator with an 8-digit output, we would calculate A equals pi r squared equals, open parenthesis, 3.1415927, closed parenthesis, multiplied by, open parenthesis, 1.2 meter, closed parenthesis, all squared, equals, 4.5238934 meter squared. But because the radius has only 2 significant figures, it limits the calculated quantity to 2 significant figures, or A equals 4.5 meters squared. Although n is good to at least 8 digits. 2. For addition and subtraction, the answer can contain no more decimal places than the least precise measurement. Suppose we buy 7.56 kilogram of potatoes in a grocery store as measured with a scale with precision 0.01 kilogram. Then we drop off 6.052 kilogram of potatoes at your laboratory as measured by a scale with precision 0.001 kilogram. Then, we go home and add 13.7 kilogram of potatoes as measured by a bathroom scale with precision 0.1 kilogram. How many kilograms of potatoes do we now have, and how many significant figures are appropriate in the answer? The mass is found by simple addition and subtraction. 7.56 kilogram minus 6.052 kilogram plus 13.7 kilogram equals 15.208 kilogram equals 15.2 kilogram. Next, we identify the least precise measurement, 13.7 kilogram. This measurement is expressed to the 0.1 decimal place, so our final answer must also be expressed to the 0.1 decimal place. Thus, the answer is rounded to the tenths place, giving us 15.2 kilogram. C. Significant figures in this text. In this text, most numbers are assumed to have 3 significant figures. Furthermore, consistent numbers of significant figures are used in all worked examples. An answer given to 3 digits is based on input good to at least 3 digits, for example. If the input has fewer significant figures, the answer will also have fewer significant figures. Care is also taken that the number of significant figures is reasonable for the situation posed. In some topics, particularly in optics, more accurate numbers are needed and we use more than 3 significant figures. Finally, if a number is exact, such as the 2 in the formula for the circumference of a circle, c equals 2 pi r, it does not affect the number of significant figures in a calculation. Likewise, conversion factors such as 100 centimeter over 1 meter are considered exact and do not affect the number of significant figures in a calculation.